All right, welcome in math class. All right, so in this video, I'm going to introduce how I expect your composition notes to be done. So here you can see I have an illustration. This is supposed to be an illustration of your composition notebook that I got right here. Okay, and on the front you're going to have Math 2020 notes, and you're going to write your name here. So for example, my name is Jake Shaheen, so I'll put Jake Shaheen. All right. Now, once you've got your title page or your cover set up, we're going to open the book. We're going to open your composition to the very first page, and we are going to open up by creating a table of content. All right. So at the top, you write 2020 Math Notes, table of content. That'll be on the very first page. In this top right corner, you'll have the page number, and we'll have a list going down here. You don't need this. We're going to skip 3 pages from this. So from here, I want you to skip 3 pages, and then 7th grade. This is going to be your first page of notes. So you're going to come up here. I just did this big old 1 up here. You're going to put a 1 in the top right corner, and that's going to tell you that that's your first page. So you're going to come back to your table of content, which is here, and you're going to write ratios, because everybody's first page is going to be ratios, the first set of notes I'm giving you. So as I mentioned, your pages from here likely won't be the same. Some of you have bigger handwriting, some of you have smaller handwriting than I do, some of you will be able to fit more on one page than I will. So from here, our pages aren't going to match up, but everybody's first page should be ratios, and we'll go from there. So, okay, so from here, I'm going to give you an explanation of what exactly is on your notes over here. All right, 7th grade. So this is going to be your first set of notes on ratios. So you'll have ratios at the top right there. And I'm just going to pull, the title is going to be ratios. So I'm just going to pull it down so I can get what I want in the frame here. Yeah, just like that. Oh, yeah, that looked good. All right, so first of all, you start with the definition of ratio. A ratio is an ordered pair of numbers which do not equal 0. That's what the little equal sign with the slash through means. Does not equal. A ratio is denoted as A colon B, where A is the first value and B is the second value in the ratio. Seems pretty straightforward. A ratio has infinite equivalent ratios, just like fractions have an infinite number of equivalent fractions. A ratio has an infinite number of equivalent ratios, just like a fraction. A to B is equal to A times C to B times C, where C is any number. So, and here's the example of this. So the letters right here, the variables may be a little abstract. Here you can see an example of a concrete example of this, where we have 5, 2, 3, which is equal to 5 times 2, 2, 3 times 2, which is equal to 10 to 6. So 10 to 6 and 5 to 3 are equivalent ratios. Ratios are read as A to B, for example, 5 to 3, and are used to describe relationships between quantities, such as miles driven and hours driving. And right here I have an example of that. So I drove 100 miles in 2 hours is a ratio of 100 to 2, which is equal to 50 to 1, because we can cut both of those in half. We can multiply them both by 1/2, if you want to say it like that, but we also could just divide them in half. So 50 to 1 is equal to 100 to 2, and again, it's describing the relationship between the miles we've driven and the hours that we've driven. So take your time, copy these notes. I'm going to go ahead and pause the video here if you need to. I'm going to go ahead and move down and keep on talking. All right, is this the whole, okay, this is the rest of the page. All right. Okay, so from here, you're going to get a definition for unit rate. All right, a unit rate describes the value of a quantity A when compared to 1 unit of the other quantity B. And that could also be flipped. It could be describing one quantity A compared to one unit of quantity B, or vice versa. You'll see some examples down here. So in this first example, I take that driving example I used up above. So I drive 100 miles in 2 hours. That gives me a unit rate of 50 miles in 1 hour. So that's the quantity of miles that I went over a 1 hour period. So it's miles to hours, or 50 miles per hour, right? Or, not of, or miles in 1 hour, or 15 miles an hour. I think that's supposed to be an hour. I don't know. Or we could say down here, or dot dot dot, 0.02 hours per 1 mile. So for every mile we drive, it takes us 0.20 hours, or 0.20 hours per 1 mile. Bonus points if you can tell me how many minutes 0.20 miles, 0.20 hours is. Great. From there, how do we calculate unit rate? Okay, now we're going to get into this first week's lessons. To calculate the unit rate of a ratio, simply divide one quantity in the ratio by the other. So, for example, if I wanted to find the unit rate of miles to hours in the example that we've been using, I drive 100 miles in 2 hours. That gives us a ratio of 100 to 2. The unit rate we could say is 100 miles over 2 hours. Well, we want that as a whole number, so, and not a fraction. So we'll just divide 100 by 2. That'll get us 50 miles in 1 hour. We discussed that previously. It's an equivalent ratio. Or we could say 50 miles per hour, where 50 is my unit rate. And you can see the little lines going down here. 50 describes my unit rate, right? 50 miles per hour is the rate, and I will use those terms interchangeably. And if you use them interchangeably, that'll also be fine. Unit rate is the number, okay? So here the unit rate would be 50. The rate would be the description of that, 50 miles per hour. Okay, so there's that. Now again, the unit rate can be described, it just needs to describe the value of one of the quantities to one single unit of the other quantity. So another way we could think about this unit rate is to divide 2 hours by 100 miles, or 0.02 hours per mile. So if we're using this as our example, 0.02 would be our unit rate. Yeah, great. And hours per mile would be the rate, the description of the unit rate. Fantastic. Take your time to copy that, and yeah, then we'll be back. 7th grade gets off the easiest for week 1 of my classes. Y'all, this is the only other page of notes I have for you, if I'm not mistaken. Okay, so in this next section, we're going to be talking about proportional versus non-proportional relationships. So you have a definition for proportional. Proportional means all unit rates in a set of data are equivalent. For example, so I make a little T-chart down here. The data set compares total cost versus numbers of shirts purchased. So this is like a chart of shirts, of a quantity of shirts that I purchased. So if I bought 2 shirts, it cost $10. Bought 9 shirts, it cost $45. If I bought 5 shirts, it cost $25. 7 shirts cost $35. Fantastic. Okay, so the unit rates for all of these, and I'm just going to divide total cost by shirts to find this. So unit rate for each one of these, so for $10 for 2 shirts, that means I'm paying $5 per shirt. 10 divided by 2 is 5. $45 for 9 shirts, well, that's 45 divided by 9, which should be $5 per shirt again. And you can see a trend starting to happen. $25 divided by 5 shirts, $5 per shirt. $35 divided by 7 shirts, $5 per shirt. So we can see all of the unit rates here are the same. They are equal. So all of these unit rates are equal. So the relationship between cost and shirts we determined is proportional at least based on the information we have, right? Great. Take your time, copy this. Good. If you're creative enough to come up with a different situation, go for it. Otherwise, please feel free to just use mine because it's already created and you don't have to think about it. Hopefully, you've maybe run into situations like this where, I don't know, like you buy a bunch of one thing and they all cost the same amount. Like you go to the little the snack stand or whatever, it's like $1 for a Coke. So if you pay $2, you get 2 Cokes, right? So the rates are proportional. I'm moving down. Okay, I want to get all of this in the front. And this should be the last little bit of notes y'all get. So, a non-proportional relationship means that the unit rates in a set of data are not all equal. They're not all equivalent. Okay? And that's the key here. Because even if some of the sets of data in your table or whatever in your data, if some of those sets are equivalent, it doesn't matter if they're not all equivalent. They all need to be equivalent for it to be a proportional relationship. So if they're not all equivalent, then we have a non-proportional relationship. Okay. So again, I'm using my example from above. This data is set compares total cost of number of shirts. It's the same deal, only the numbers change a little bit. So here, 2 shirts cost $10, 20 shirts cost $90, 10 shirts cost $45, 3 shirts cost $15. So we come over here, we do the unit rate comparison. $10 divided by 2 shirts, that's $5 per shirt. But $90 divided by 20 shirts gets me $4.5 or $4.50 per shirt. So if the question was, are all of these ratios proportional? Is the cost proportional to the number of shirts? Well, the answer would simply be no. We already know that because one of these unit rates is not equivalent. Two of these unit rates are not equivalent. So this is a non-proportional relationship, no matter what. All right. So we can use unit rate to compare ratios. This is what we did here, right? So which one of these deals is a better deal on shirts, right? You might not have $90 or $45 to spend on a shirt, but if you do, you can get more bang for your buck. You can get the shirts cheaper, essentially. What's a better deal? 10 shirts for $45 or 3 shirts for $15? $4.50 is less than 5, so 10 shirts, $45 is cheaper deal per shirt. Again, you might not have $90 to budget or $45 to budget on a shirt. But anyway, take your time, make sure you get all these notes, and I think this is it. So I'll see you on the next one.